lessons. We'll probably just cover the first half of it here today because these two lessons are kind of interlinked with each other just because of the concepts that we'll be covering here today. So in 3.1 and 3.2, we have been doing scatter plots, taking a look at patterns of bivariate data and taking a look at the strength and the direction and the form of those patterns. So yesterday we talked about correlation coefficient R and how that helps us measure the strength and direction of a linear relationship. So now we're going to take that linear relationship to yet another level, and we're actually going to talk about its equation. Okay? So the equation to a line of best fit is sometimes called a regression line. Okay? So it just basically is a line that we use to basically find a response variable when given an x variable. So how does that y change at any given x? Regression equations will take this particular form. Down here, we write it in this form, y equals a plus bx. You can write it other ways, but for our course and our textbook, and even our calculators will do more than one way. But for what we will refer to, I will always refer to y hat equals a plus bx. Y hat stands for the predicted value or the predicted y. So sometimes let's say y hat represents the predicted y value. And this is very important to decipher y hat because later on we'll talk about what we call our observed y, and that's just the plain old y. Then we have our slope. That's the b value right here. There's our slope. So back in our algebra days, algebra 2 days, we've been dealing with slope. Slope, again, okay, is how the y predicted change when x increases by 1 unit. So remember, it's the change in y over the change in x. And specifically, we'll look at how much does our predicted y change for every one x value. So we're going to talk about that, especially when we talk about our interpretation of slope. The last part is the a value. A is simply your y-intercept. Basically, where does your line cross the y-axis? Basically, what is your predicted y value when your x value equals 0? This definitely helps when we graph it, but sometimes you got to be careful in that sometimes your y-intercept is not really a reliable or useful value in the context of the problem that you're analyzing, because it might not make sense to have an x value of 0, or the predicted y value that you get when x is 0 doesn't make sense in the context of the problem. When that sometimes happens, we can have sometimes what we call extrapolation. And you may have heard that word maybe in a social studies class before. Extrapolation is where we get results, or we use a regression line to predict something that is outside our data. When you are using a regression line, you might have some data here. I'll make a nice kind of positive linear pattern. When you have your prediction equation, you want to make sure that your prediction equation only uses your x values in between the interval that the equation was derived from. Going outside of that is what we call a form of extrapolation, because what will happen is from time to time it's going to produce results that either A, don't make sense, or results that are just very unrealistic. So to put this in action and just to kind of go through some examples here of slope and y-intercept and actually to see extrapolation, let's take a look at this first example here at the bottom. So first of all, it says some data were collected on the weight of male white laboratory rats for the first 25 weeks after birth. A scatter plot of the weight in grams and time since birth in weeks shows a fair, strong, positive linear relationship. Okay? So if we have a fair, strong relationship, it's basically looking probably something like this. What variable would be on my x-axis? What are we actually comparing here? Said collected on the weight, and then it said for the first 25 weeks. So what variable is going to go on the x of these two? Is it going to be weight or time? Okay, so the time or the number of weeks. And it's really number of weeks after birth. What's going to go on the y-axis?
Their weight.
Their weight. So a lot of times when you do these problems, like it says here, it says the linear regression equation written below models the data fairly well. So they give you the actual regression equation. Probably one of the most important things to do right away is to actually define what is x and what is y hat. Because if you don't know what x is and if you don't know what y hat is, interpreting the context and the y-intercept and what we're talking about, it's not even going to make any sense. So again, our x is the number of weeks after birth, while y hat is the predicted weight of a lab rat. Bless you. So right away when I do these problems, that's probably the first thing I do is I need to figure out, all right, what is x and what is y? Jack, you need a pass? No. Okay. All right, have a good day. Now that I have those, I think the next question asks, what is the slope of my regression line? Well, what's its value? According to this equation, what's my slope? Okay, so my b value is 40. Number in front of the x is the slope. What does this actually mean in our context? So, if I go back up to what slope is talking about here, the amount in which the predicted y changes basically when x increases by 1 unit. So, the predicted y, the predicted weight of a lab rat, so the predicted weight of a lab rat goes up by, what's my unit of measure?
Grams.
Grams. So 40 grams for each x value, and my x value is for each week after birth. Or I could say just for each additional week after birth if I wanted to. So each 1 week, for every week after they're born, they're going to gain 40 grams of weight. Thank goodness it's not pounds.
40-pound rat.
Yes.
I'd be terrified.
Have you ever seen The Princess Bride?
That's true.
Oh my god, yeah.
There you go. Rats of unusual size. Alright, what is the y-intercept? Alright, so the a value is 100. So, at this case, y-intercept is when x is 0, y is 100. Well, what does it mean in this context if x is 0? How old would the rat be? It wouldn't be dead, it would just have been born. So, at birth, the predicted weight of the lab rat is 100 grams. Now notice how I'm saying predicted weight. I'm using that word predicted. It's not the actual or the observed value. Okay? It is the predicted. Alright, so now, are we okay with how we interpret slope and how we interpret y-intercept? I'm okay, you're okay? Alright, good. We're all okay. Alright, so now, C says, predict the rat's weight after 16 weeks. So it says, predict the rat's weight. What variable is that? Of my two variables, which one is that? Is that x or y? That's the y hat. Because it says predict, so put that little hat symbol or that little caret above the y. After 16 weeks, what's that variable? 16 weeks stands for?
X.
X. Beautiful. So now let's plug it into our equation. So I have y hat equals, according to my equation, it's 100 plus 40 times my x. I'm replacing the x with 16. So 16 times 40 plus 100 tells me that my y hat is 140 grams. Okay? So, the predicted weight of a lab rat at 16 weeks is 740 grams. So, 740 grams, is that a lot?
Yeah.
Does that weigh like a lot of weight? Well, yeah. Well, what's nice about D is at the very bottom here, I'm just kind of going to use this note, 1 pound is the same as about 454 grams. So, 740 grams, 454 goes into it, a little bit more, somewhere between 1 and 2 pounds. Is that really heavy for a rat? 1 to 2 pounds for a lab rat, you know, big white lab rat might get to be about that big, might be okay. However, let's take a look at D. Again, this is a lab rat, not a sewer rat. Right? Because I know that when we do D, some of you might say, well, sewer rats sometimes get this big. So it says, should you use this line to predict the rat's weight at age 2 years? Well, what does 2 years equal in weeks?
104.
4 weeks. Again, 52 weeks in a year times 2, 104 weeks. Should you use this equation to predict it?
No.
Why? Okay, well, they're going to stop growing, and likewise, what did they say this equation's interval was? For the first 25 weeks. So, should you use this equation? No. This equation is only, I'm going to move this up so I can write a little bit higher, reliable for, oh, how do I want to say it now? Is only reliable for weeks 0 through 25, and 104 weeks is well outside this interval. It will most likely give me an unrealistic result. In fact, we're going to actually see what this predicted result would be. So, if I were to put in 104 here, $104 times 16 plus another 100. How much is that? Wow. It would be like 1,000. Whoa, it would be like more than that, wouldn't it be?
Yeah, why?
1,740 grams? Is it? Oh, I'm sorry. I'm like looking at this too. Thank you. My apologies. Why was I was putting 16 because it was 16 weeks before. Sorry about that. Because this one I was doing 16, but it should be 40. There we go. 4,260 grams.
That's like 9 pounds. Yeah, it's just above 9 pounds.
Okay, which is about 9.38 pounds.
That's weird.
That is one big lab rat.
That's like the size of a newborn baby.
Yes. That is actually a great analogy, Carter. I like that. That's the size of a heavy newborn baby. Okay. Most babies are usually right around 6 to 8 pounds. So I know my daughter was 6'11". I was 8'0". Some of you might know your own birth weights. So we're talking, now I know my stepdaughter, she was like, I want to say 10 or 11 pounds. So she was really big. Hence why my daughter was taken as a C-section, because they were worried about my daughter's weight.
My mom just reminded me that my head was 3 centimeters too big.
Was how much too big?
3 centimeters too big.
3 centimeters too big. Oh boy.
She will never let that go.
She won't. Alright. Let's take a look at our next page and our next example. You will definitely want to have your calculators out, because we're going to use our calculators quite a bit for this problem. So make sure you take those out.
I know, but I like to do
So if you ever wonder what I do in my spare time, here's an example. Mr. Parts does an experiment with his Hot Wheel car. Yes. Where he wants to see how far it will fly through the air depending on how high the start of the jumping ramp is. I'm really curious about this. He has the same car go down a ramp at different starting heights and records how far they traveled in the air in inches. The data he collected is noted below. Height of the ramp in feet, distance in the air in inches. So, in number 3, it's asked us, or I'm sorry, in letter A, we have 3 things to do. It asks us to make a scatter plot of the data. It asks us to find this LSRE, which stands for least squares regression equation. And then least squared regression line, so this would be least squares regression line. You will see our textbook use these acronyms. LSRE, which is just a fancy name of saying find the regression equation. And LSRE, which is a fancy acronym for, well, draw the line to the regression equation. We're going to show you how you do this on your calculator today. And we'll talk even in more detail about these equations and how we get them. So, first of all though, it wants us to make the scatter plot. Alright, so I'm going to draw X and Y axis real quick here. X, Y. My X is my height of the ramp. And my height of the ramp is in feet. And this is distance in the air in inches. So as I'm continuing to work on this here, I look at my height and it's going from 1 foot all the way up to 5. So you know what's nice is I'm going to actually start that at 0 and count by halves. So I got 1, 2, 3, 3.5, 4, 4.5, 5. So again, making our scatter plots, we want to try to use all of the x-axis. Distance in the air. 3 inches all the way up to 45 inches. So I might count by 5s here. 5, 10, 15, 20, 25, 30, 35, 40, 45. Wow, nice. For once I number one nicely that I use the whole graph and I don't have to squeeze. Here's the first, huh? So I'm going to start graphing my points. 1, 3. 1.5, 7. 2, 12. 2.5, 18. 3, 23. 3.5, 28. 4, 32. 4.5, 38. 5, 45. Wow. Would you say we probably have a pretty strong positive linear association going on here?
No.
No?
Absolutely not.
It's starting to look that way, but okay, the question becomes, how do we find this least squared regression equation? So this is a function on your calculator that you should know, love, and make your best friend. We've actually been using its, I'll say, counterpart or its cousin when doing correlation yesterday. Okay. What you want to do is on your calculator, you're going to go to your stat menu. You're going to use your right arrow. Under the menu calculate, we're going to choose number 8. There are 2 linear regression pieces in your calculator that you can choose. You can choose number 4 or you can choose number 8 when getting the correlation. We use the equation for 8 for the linear regression because it uses A as the y-intercept and it uses B as the slope. Now, before I can actually get the equation, guess what I actually have to do first?
Turn on your diagram.
Well, even before I turn on my diagnostics, what do I have to do?
Put everything in.
I gotta put in my data, don't I? Do you have your data in yet?
Yep.
Okay, some of you are ahead of the game. Awesome. But let's take a minute. Let's enter in the heights of the ramp in list 1. Enter in the distance in the air in list 2. I've already done that. So those of you who are watching the video at home, pause your video and enter it in.
Are you recording right now?
I am recording right now.
Hi, Mom.
Yes, thanks.
Thanks, Daniel.
Does anyone need more time to enter in your data? Speak now. Okay.
Hello again.
Hello again, yes. Alright, so we have our data in. Just as I stated with the commands. Stat. Use your right arrow and highlight calculate. I know there's a number 4 here that says ln reg ax plus b, but this has a as the slope and b as the y-intercept. So if you can decipher the difference, by all means use number 4, but I will always refer to a as the y-intercept and b as the slope. Hence why I choose number 8. See how it has a as the y-intercept and b as the slope? Okay, so now, if your data is in list 1 and list 2, you can hit enter. If it's in different lists, you actually have to type those lists separated by a comma. And we'll try to demonstrate that if I get to the other example today. So go ahead and hit enter. Wow! Not only does it give us our correlation coefficient, which will be a question later in this problem, but here's my slope, and here's my y-intercept. Now, the question becomes, a lot of students will ask, well, how many decimal places should I go out? Because both these decimals keep on going on forever, just like today's lesson. My jokes are never too old. Okay. Now, thanks, Evan. I remember that. You didn't think I heard you. I wonder if the people watching the video did. I hope they do too. Anyway, getting back to this, I look at what the data represents. And since it's representing height and distance in feet and inches, and since the height of the ramp was given to me in at least 1 decimal place, I'm probably going to go out 2 in both instances and round them. So, for my equation, I'm writing y hat equals negative 8.21 plus 10.37x. Now again, I've just written the regression equation, but that's not just enough. I better write what x represents and what y hat represents. So x represents, look on your x-axis, the height of the ramp in feet. Oops, I forgot the height there. Y hat represents the distance in the air And I might even say of the Hot Wheel car. In inches. It's very, very, very important to be able to identify your variables. All right, now we have our variables. Let's start, or I should say our equation, and we've identified what our variables represent. So now that we know that, let's continue answering the questions. It says, interpret the slope of the least squared regression line or equation in context. So what was the slope value here? What was my B value? 10.36 or 37. Ooh, and I forgot to graph the line, so I gotta go back. But that's okay. We'll do this and go back to it. I forgot something. I get so excited to answer the rest of the questions. Just like students sometimes, I forget to answer one of the parts. So, what does 10.37 actually mean in the context? Well, for each additional 1x, this is what my y value is going up by. So, for each additional 1 foot in ramp height, Mr. Bartz's Hot Wheel car will travel 10.37 inches in the air. Nice. So if I can make that ramp height like 1,000 feet tall, that Hot Wheel car is going to go flying. If it's not working, William, grab a pencil out of my pencil jar for now and we'll fix it later. Alright, so now I'm actually going back up to A for a minute because Mr. Bartz forgot to do something.
Oh no.
Wow! Boo, Mr. Bartz!
Boo.
Okay, you get a boo me on the video. It asks you to graph the least squared regression line on your scatter plot. Okay? So, first of all, how am I going to graph this? Well, how many points does it take to graph a line? 2 points. So what I have to do is figure out what 2 points can I use to graph this least squared regression equation. Well, if I look at my equation itself, what's a point that I know that's going to be on my graph that I can easily find just by looking at the equation? Okay, this is a slope. Is that going to help us? No. How about this? This negative 0.821. What is this?
Y-intercept.
Y-intercept. What does y-intercept actually mean?
X is 0.
Okay, so when x is 0, isn't this y?
Yeah.
So as I think Charlie, you were saying, is where it crosses the y-axis?
Yeah.
Yeah. So, right now, I'm going to extend my x-axis down here and go -5 and -10. And I know that one of my points on the axis is located at, and I'm just going to estimate it, -8.21. But now I need to get one more point. Now, to get this other point, I am going to jump ahead in the notes a little bit. Okay. Ooh. So turn to the next page of the notes. Okay. I'm going to talk about this concept of residuals in a little bit, but here is the formal definition of your least squares regression line. The reason why it's called least squared regression line, I will actually go into in a few minutes after I talk about residuals. Okay? But it's basically your line of best fit. There's an actual mathematical reason why it's the best. Okay? Now, this particular equation has some facts about it that you should know. Okay? And these are three things that are important to know. First of all, it is unbelievably important, okay, that you make a distinction between the explanatory and response variable. Okay? We've defined what the explanatory variable was and the response variable. We've actually done that. And it's very important to do that, because if you flip them around, you are not going to get the same equation. Now, later on, what we're going to see here is there is a close connection between correlation and slope. Okay? They are related to each other in that if the slope is positive, so is the correlation. If the correlation is positive, so is the slope. And vice versa, meaning if it's negative and negative. They're connected that way. The last part is what we're going to use for the graphing. Okay? And that is this. The regression line will always go through the point mean of x, mean of y. So if you have your data, if you can find the mean of the x values, and you can find the mean of the y values, it will always go through that coordinate. So we're going to take that fact, go back a page, and we're going to find that point. So this first one here again was the y-intercept. The second point we're going to use is the mean of x, mean of y. Well, I have my data in my calculator, which is nice. So what I can do is go stat, calculate, and instead of doing one variable statistics, I can go down to number 2 and do 2 variable statistics because I have a relationship here between x and y. In the past, when we tried to do it with one variable, it wouldn't work because we had more data points of one and the other. So if you select 2 variable statistics, right now, since mine is in list 1 and list 2, it defaults to it. It will give you your mean of x. Look at that. Mean of x is 3. Scroll down. Ooh, look at that. Mean of y, 22.8 repeating. So let's note those. We got our second point. 3, 22.89. So now, the best of my ability, I'm going to graph that point to 22.9. And now I'm going to try my best that I can to connect those 2 points. Woo! Not bad. Oh, don't worry. We still got about an hour's yet to go.
Oh, joy.
Now, if I want to see how well I drew my sketch by hand, I'm going to check it versus my calculator. So, a couple things I can do. First of all, I want to do my scatter plot. So second y equals, I'm going to turn on the stat plot, and many of you probably already have this set to be on scatter plot in list 1 and list 2. You might have list 3 and list 4 here. You just have to go down and change them. So if you have your scatter plot in, go ahead and go zoom 9. Does my scatter plot look like what I have graphed over here?
Yeah.
Yes.
Yes.
So now I want to put in that line or the least squared regression equation and get my line. So go to your y equals and type in the equation. Negative 8.21 plus 10.37 x. Got to put the x in, otherwise it doesn't become a slope. Hit graph. Woo! How's that looking?
It's like exactly.
Pretty darn good, isn't it? It ain't bad. These points I probably could have been on it a little better, but the upper points did pretty well. Looking pretty solid. Sweetness. Alright, so let's finish up our last couple problems here. So in C, it says, find the correlation and interpret its value in context. Notice how we're asking you to do a lot of interpretation. That is probably one of the biggest things in statistics we ask you to do, is not only be able to calculate it out, but know what it means and be able to explain what it means. So when we go back to that correlation coefficient, when we did our least squared regression, we did this stat calculate number 8, just kind of going back to it. Lots of times I'll actually write down what R is right away, just in case it comes up. Look at that R value, 0.9985 if we round it. Wow. Is that pretty darn close to 1? That's probably the best one we've seen, isn't it? I think so. So what does that mean? Well, we have a, what words should I use for strength?
Moderately weak.
Strong.
Very weak.
How about very strong?
Mr. Bartz equals strong.
That is true, I do equal strong. We have a very strong positive linear association. Of course, we could have said correlation or relationship, that would be fine, between the ramp height and the distance traveled by Mr. Bartz's Hot Wheel car. We are recording this video right now.
Joachim!
Thank you. That just saved us from a lot.
Oh, it would have been so much fun.
It might have been. But it saves all the people who are sick and gone who have to watch this.
But they should have come in. They missed the fun.
They missed the fun. Alright, D. Find the predicted value, the distance traveled in the air by the car when the ramp is 4 feet. Okay, let's do that. So, y hat equals, again, our equation, negative 8.21 plus 10.37x. We want to find the predicted value. We want y hat. When the ramp is So, oops, sorry, 4 feet high. So that's our x. So y hat equals negative 8.21 plus 10.37 times 4. So if you plug that in your calculator, did anyone get it? It's like 33 something or something like that. 33.23. Do I have a second on that?
Second.
And what units is it?
Second motion.
It's inches, right? So I'm just going to note here, if the ramp height is 4 feet, the predicted distance traveled by the Hot Wheel car is 33.23 inches. All right. The last question up here says, what is the value of the residual at a ramp height of 4 feet? It says up there tomorrow, or in parentheses, tomorrow. I will wait till tomorrow to talk about residuals. So we will stop right there. I'll stop our wonderful video. I know you guys are bummed.
Bye.
Say goodbye. Bye.